Welcome to Programming Problems for Advent of Code Day 19, where we will look at Aplenty. Let's start. The elves are busy sorting machine parts and they need our assistance. Each part is rated in 4 categories. The categories are extremely cool-looking, musical, aerodynamic, and shiny. The sorting process involves workflows with rules that determine whether a part is accepted, rejected, or sent to another workflow. If a part gets accepted, its rating number is the sum of its ratings across each category. Now, the main question for Part 1. What is the sum of all of the rating numbers for all of the parts that get accepted? Let's have a look at an example. On the left, you see the workflows that are provided as an example. On the right, you see those same workflows visualized in a tree. Every dark blue cell is the label of a workflow, and the colored blocks help us decide whether a part should be redirected to a different workflow or whether it is accepted or rejected. For convenience, I colored blocks which mark a part accepted green and those that reject a part red. Determining acceptance of a part then works as follows. You get a part from your input and we start at the workflow labeled in. Then we go to the first step in the workflow, which asks us to compare the S property of our part. If the statement evaluates to true, meaning that S of the part is smaller than the number in the step, then the part would be redirected to a different workflow. However, our part's S value is larger, so we go to the next step. This next step simply redirects us, so we start with the next workflow. Here we again are asked to check for the S property, and this time we are redirected. The next step is not true, so we continue and let's skip to the next workflow. Here we find that M is indeed larger than 1,548, so this part is accepted. Its rating is 7,540. We can iterate over all parts in our input and sum the ratings accordingly. Do you see how to do this in code? Let's look at the solution for Part 1. Our solution outline is to create a network of workflows and conditional transitions. After parsing the inputs and thereby obtaining our network of workflows, we loop over every part and we check if it is accepted. If it is, we add the sum of all its values. Before we parse the inputs, let's first strengthen our understanding of how we will model our workflows and steps. Checking if a given part is accepted requires us to start at the workflow labeled in, and then while the ID of the workflow is not rejected or accepted, then we would like to be able to just apply the workflow to the part and get the next ID. At the end, we just need to return if the final ID is accepted. Let's make it possible to apply a workflow to a part. I opted to define a class which can be initialized from the input. The input provides a name or the ID and then one or more steps. The last step in the data is always just a simple redirect, which we'll store explicitly. The apply function then loops over the steps to see if any of them evaluates to true given the part. If none of the individual steps apply, then we redirect to the element of the workflow. In the example at the bottom, this would be a redirect to the rejection state. The steps of the workflow which we've seen just now can be modeled as a basic class for which the apply function just returns a Boolean. See the blue steps of the workflow on the right. Every step has a key, for instance S or M, an operator, and a value to compare against. Though not shown explicitly here, every condition in a workflow of course also has a redirect label associated with it. And that was all there is to the logic of Part 1. All that's left is tying it together by parsing the inputs. Today's problem provides 2 lists so we can find the split and then parse the workflows and parts separately. For parsing the parts, I opted to just converting the input to Python dictionaries. Last but not least, we parse the workflows. We can represent this as a dictionary where the labels of each workflow is the key for easy lookup. The redirects from every step or workflow form the links. And that was it again for Part 1. Let's continue. Even with our help, the sorting process isn't fast enough, so the elves come up with a new plan. Rather than sorting parts individually, maybe we can figure out in advance which combinations of ratings will be accepted or rejected. Each of the 4 ratings can have an integer value ranging from a minimum of 1 to a maximum of 4,000. How many distinct combinations of ratings will be accepted by the workflows that we've been given? If we look at the example of Part 1 again, then we're told that this network will accept a number of combinations that is mind-boggling. For the rest, there are no hints provided. Do you know how to solve this one? Let's take a look. First off, the total number of possible parts to check is enormous, so the key to part 2 is to find a way to improve efficiency. The key concept of how you can do this is to process ranges of parts as opposed to individual parts. Here we consider the first workflow of the example, and we can say that the parts which we consider are all the parts, as indicated by these ranges. Then, at every step in this workflow, we can split up the ranges of the part properties as indicated by the value of the step. So the parts which we split off to the bottom are all parts which have an S value between 1 and 1350. The solution outline then changes as follows. Let's update our representation for a part to be a tuple of integers, indicating the lower and upper bound of a range. Then we of course only need to parse workflows from our input. As seen on the previous slide, we'll then start with an initial part, which represents the full range of possible part combinations, and will process the parts and workflows to give us back a total number of combinations. The application of our concept looks as follows. Every part will process as part of a queue and will split them once at every step. Each split might return 0, 1, or 2 new ranges of parts. The simple case is where we'll grab something from the queue, and we then see that the ID is accepted. In this case, the part represents some total number of combinations which will add to the total. Alternatively, if the ID is not rejected, then we'll look up the workflow and we'll apply the workflow, which will split our range into 1 or 2 new parts, which will append to the queue accordingly. Having the workflow split apart works as follows. Given a part, we'll check for every step if it is applicable. At the first step that is applicable, we'll split the range into 2 segments. The first one is the segment that should continue to be reprocessed by the current workflow later on. The second one is the segment that immediately gets redirected. If at the end none of the steps applied, then the part needs to be redirected to the label that is at the end of the workflow. Note that for simplicity's sake, this apply function always only applies a single split, even if multiple steps would theoretically apply to the given input range. The conditional also needs some updating. First, we check if it is applicable to a part. For this, we just check that if we were to apply the less than or greater than operator to the part, that we would actually split the range on the given property as indicated by our key. If it does, then we can apply the split. So given a part, we'll make 2 copies of the dictionaries and we update the ranges according to the value of the conditional. Then we return parts 1 and 2. Which one is redirected and which one needs further processing by the workflow is left up to the workflow class. Then finally, after the queue is done processing all part ranges, we are left with the task of determining the total number of combinations that a single part range represents. This is simply the multiplication of each of its 4 property ranges and can be computed as shown. And that was it once more. 2 more stars. Thank you for following along and please subscribe if you're interested in seeing more content like this. See you at the next one.